I want you to do something very simple. I want you to look at a lamp in the room or a light bulb, and I want you to reach over to the switch and flip it on. Click, and there it is. The room is full of light. Instant. Immediate. It feels simultaneous. Your finger moves, the light appears. There is no gap. There is no waiting. It feels like light is everywhere all at once. For thousands of years, human beings, very smart human beings, much smarter than you and me, they thought that light was instantaneous. They thought the speed of light was infinite. And why wouldn't they? If I throw a rock at you, you see me throw it, you see it coming, and then bonk, it hits you. You can watch it travel. But light, you open your eyes, and the distant mountains are just there. You don't see the image of the mountain traveling toward you. It just seems to exist. But nature is tricky. Nature holds her secrets tight. And usually when our common sense tells us something is obvious, nature is waiting around the corners to hit us with a pie in the face. Because light does travel. It moves. It is a thing. It is a traveler. And the story of how we found that out and why it moves at the speed it does is perhaps the greatest detective story in the history of science. So let's go back. Let's go back to Galileo. Now, Galileo was a man who didn't take anybody's word for anything. If Aristotle said heavy things fall faster, Galileo said, let's throw them off a tower and see. So Galileo, he suspected that light had a speed. But how do you catch something that fast? He came up with an experiment. A very simple, very human experiment. He got two guys with lanterns. He put one guy on a hill. He put the other guy on another hill, maybe a mile away. The plan was this. Guy number one uncovers his lantern. Flash. As soon as guy number two sees the light, he uncovers his lantern. Flashback. Galileo stood there with a timer, a pulse beat or a water clock, and he tried to measure the delay. He tried to measure how long it took for the light to go there and come back. And what did he find? Nothing. He found that the light was too fast for his reflexes. The delay was 0. Or at least the delay was so small that it was masked by the time it took for the guys to just move their hand. So Galileo failed, but he was smart in his failure. He didn't say light is infinite. He said, if it has a speed, it is extraordinarily fast. Faster than I can measure on a hilltop. He realized that a mile is nothing to light. A mile is a joke. To catch light, you don't need a bigger hill. You need a bigger laboratory. You need space. And this is where the story gets wonderful. We move to the year 1676. A Danish astronomer named Ole Rømer. Rømer wasn't looking for the speed of light. That's how science works usually. You are looking for the bathroom and you find a gold mine. Rømer was looking at Jupiter, specifically the moons of Jupiter, Io, the little moon Io. Now, the solar system is a great big clock. It is the most precise clock we have. Now, Io goes around Jupiter, round and round, and every time it goes behind Jupiter, it gets eclipsed. It disappears, and then it comes out the other side. It's regular. Tick-tock, tick-tock, tock. It happens every 42 and a half hours. So Rømer is watching this, and he's writing down the schedule. He's making a timetable. Okay, the next eclipse should happen next Tuesday at 9 p.m. But then something strange happened. When the Earth was close to Jupiter on the same side of the sun, the eclipses happened right on schedule. But 6 months later, when the Earth swung around to the other side of the solar system, moving away from Jupiter, the eclipses started to be late, and they were lagging behind, minutes late. And then as the Earth came back around closer to Jupiter again, the eclipses caught up. They got back on schedule. Now, most people would have said, oh, my clock is broken, or Jupiter is wobbling. But Rømer, he had an imagination. He had a physical intuition. He said, wait a minute. The moon isn't late. The news is late. Think about that. The news is late. He realized that the light, carrying the image of the moon, the picture of Io coming out from behind Jupiter, it had to cross the gap between Jupiter and Earth. And when Earth is on the far side of the solar system, that gap is bigger. It's an extra 186 million miles or so. The light had to travel that extra distance. And that took time. It took about 16 minutes to cross the width of Earth's orbit. Rømer did the math. He divided the distance by the time, and for the first time in human history, we had a number. We knew that light was not magic. It was a messenger, and the messenger had a speed limit. It was fast. Oh, it was terribly fast, but it was finite, and that changes everything. Because if light yet takes time to travel, it means when you look at Jupiter, you're not seeing Jupiter now. You're seeing Jupiter as it was 40 minutes ago. When you look at the sun, you're seeing it 8 minutes ago. If the sun blew up right now, we wouldn't know it for 8 minutes. We'd be sitting here on the beach, happy as clams, while the sun was already dead. You look at the stars, you were looking at ancient history. We are trapped in a bubble of the past. We can never see the now of the universe. We can only see the then. So we found out it moves. But that brings up the next question, the big question. The question that leads to the title of this talk. What is it? What is moving? Is it a stream of particles, like little bullets? Newton thought so. He called them corpuscles. Or is it a wave, like sound, like ripples in a pond? This was the great war of physics for 200 years. The particle guys versus the wave guys. And in the 1800s, it looked like the wave guys had won. We did experiments, the double-slit experiment that showed light interfering with itself, wiggling, canceling out. Only waves do that. Bullets don't cancel each other out, they just pile up. So, okay, it's a wave, but a wave of what? If I shout at you, that's a sound wave. What is waving? The air. The molecules of nitrogen and oxygen are compressing and expanding, shoving each other. If I make a wave in the ocean, the water is waving. You see, common sense says, to have a wave, you need a medium. You need stuff to wiggle. You can't have a wave in nothing. That doesn't make sense. A wave is a property of a substance. So the physicists of the 19th century said, okay, light is a wave. It travels through the vacuum of space. But space can't be empty. It must be filled with a fluid. A mere subtle, invisible jelly that fills the entire universe. And they called it the luminiferous ether. The ether. It sounds like something from a fantasy novel. They said this ether was everywhere. It was inside your head. It was between the stars. It was stiffer than steel because light travels so fast. The medium must be very stiff to vibrate that quickly. But it was thinner than air because the planets moved through it without slowing down. It was a magical substance invented to explain the wave. And everybody believed in it. It had to be there. But then came a man named James Clerk Maxwell. Now, Maxwell wasn't looking at light. Not at first. He was looking at electricity and magnetism. Before Maxwell, we knew about electricity, sparks, batteries, lightning. And we knew about magnets, compasses. But they seemed like two different things. But experiments started to show that they were connected. If you move a magnet near a wire, you create electricity. If you run electricity through a wire, you create a magnet. They were like two sides of the same coin. They were dancing with each other. Maxwell, he sat down and he wrote equations. He tried to describe this dance mathematically. He found that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. So imagine this. Imagine you wiggle an electron. Just shake it. That creates a changing electric field. That changing electric field immediately creates a magnetic field next to it. But that magnetic field is changing too. So it creates an electric field next to it, which creates a magnetic field, and so on, and so on. The fields pick themselves up by their own bootstraps, and they fly away from the electron. They travel through space, self-propagating. Electricity creating magnetism, magnetism creating electricity, a chain reaction, a wave. Maxwell looked at his equations and he asked, how fast does this wave go? He calculated it based on the strength of magnets and batteries, just pure numbers from the lab, and out of the paper popped a number, 300,000 kilometers per second. Maxwell must have fallen off his chair. Because that number was exactly the number Rømer and the others had measured for the speed of light, it wasn't a coincidence. Maxwell realized the great truth. Light is an electromagnetic wave. The light you see, the colors of the rainbow, the warmth of the sun, it is just electricity and magnetism vibrating in empty space. And this is where the mystery gets deep, because Maxwell's equation gave us speed, v, the constant. But speeds usually depend on who is looking. If I am on a train going 60 miles an hour and I throw a ball forward at 10 miles an hour, to me the ball is going 10. But to you, standing on the ground, the ball is going 70. 60 plus 10. Velocities add up. That's how the world works. So, physicists thought, okay, light travels at sea through the ether. So if I am in a rocket ship moving through the ether and I shine a flashlight forward, the light should go faster. Or if I move away from the light, it should catch me slower. They built a machine to measure this. It's the Michelson-Morley experiment, the most famous failed experiment in history. They measured the speed of light in the direction the Earth was moving, and they measured it sideways. They expected a difference. They expected to see the wind of the ether blowing past the Earth, and they found nothing. Zero. No matter which way they pointed the machine, no matter how fast the Earth was moving, the speed of light was exactly the same. It didn't make sense. Imagine you are running down the street at 15 miles an hour, and a car passes you at 30 miles an hour. To you, the car is only going 15 miles an hour faster than you. But nature was saying, no. If you run next to a beam of light, it still passes you at the speed of light. You can chase it in a rocket going 99% the speed of light, and the beam still flies away from you at exactly c. It's as if you were standing still. How can that be? How can a speed be the same for everyone, no matter how fast they are moving? The math was broken. The intuition was broken. The universe was playing a joke on us. And for 20 years, the physicists sweated. They twisted themselves into knots trying to explain it. They said, maybe the rulers shrink when you move. Maybe the clocks slow down. They were getting close. But they were afraid to take the final step. They were afraid to throw away the ether. And then a clerk from the patent office in Bern, Switzerland, picked up his pen. A young man, Albert Einstein. He looked at the problem and he said, what if the experiment isn't wrong? What if our idea of time is wrong? This is the hinge of history. Einstein said, let's assume Maxwell is right. Let's assume the speed of light is constant. It is the law of the universe. V is fixed. If speed is distance divided by time, and if the speed can't change, then the distance and the time must change. Boom. Relativity. To keep the speed of light constant, space itself must squish, and time itself must stretch. If you move fast, your clock ticks slower. Your ruler gets shorter. Not as an illusion, as a physical reality. Why is light so fast? Or rather, why is light the limit? Because light is the speed at which the universe communicates. And to understand why it's a limit, we have to talk about what speed really means. We have to talk about causality. Because it turns out the speed of light isn't really about light at all. Light is just the thing that happens to go as fast as possible. The speed limit, c, is the speed of cause and effect. But I'm getting ahead of myself. Let's stop and think about the why. Why 300,000 kilometers per second? Why not instant? Why not a million? Imagine if the speed of light was infinite. If light was instant, then every event in the universe would happen simultaneously to every observer. You would look at the sky, and you wouldn't see the past. You would see the present. But more than that, if signals could travel instantly, gravity would travel instantly. If the sun disappeared, the Earth would fly out of orbit instantly. It seems nice, tidy, but Einstein showed us that if you can send signals instantly, you can send signals into the past, you break the timeline. If you can go faster than light, there are reference frames, ways of looking at the universe where the effect happens before the cause. You die before you're shot. The glass breaks before you drop it. You answer the phone before it rings. The universe, above all else, seems to want to protect the narrative. It wants to make sure that A happens, then B happens. So there must be a limit. There must be a maximum speed, That information can ripple through the fabric of reality. We call it C, and light, because it has no mass, because it carries no baggage, it goes at the limit. It puts the pedal to the metal and goes exactly as fast as the universe allows any information to move. It isn't that light is special, it's that light is lightweight. Literally, it has zero mass. So, the question, why is light so fast, is actually the question, why is the universe built with a speed limit? And to answer that, we have to look at what happens when you try to fight it. What happens if you try to push an electron to the speed of light? We do this. We do this every day in accelerators, like the Large Hadron Collider. We take protons and we kick them. We pump energy into them. They go faster, 90% the speed of light. We kick them again, 99%. Kick them again, 99.9%. Kick them again, 99.999999%. We pump enough energy into them to light up a city. And do they reach the speed of light? No. They get closer, but they never touch it. Why? Because of E equals mc squared. Energy and mass are the same thing. When you give energy to an object to make it move, you're actually making it heavier. Well, not heavier in the sense of putting it on a scale, but it gains inertia. It becomes harder to push. The faster it goes, the heavier it gets. So you need more energy to push it faster. But that energy makes it even heavier. It's a vicious cycle. As you approach the speed of light, the mass of the object approaches infinity. To reach the speed of light, you would need infinite energy. And there isn't infinite energy in the universe. So matter, you and me, the spaceships, the protons, we are trapped. We are condemned to live below the speed limit. We can never reach the horizon. But light, photons, they cheat. They have no mass. They start with zero, so they don't have to accelerate. A photon doesn't start at zero and speed up to c. The moment a photon is born, when an atom jiggles and spits it out, it is already going the speed of light, instantaneously. It cannot go slower. If it exists, it moves at c. If you slow it down, it dies. It gets absorbed. So light lives on the edge. It lives on the boundary of reality. And living on that boundary, things get very, very strange for the photon itself. Have you ever wondered, what does the universe look like to a beam of light? If you could ride a photon, what would you experience? This is a thought experiment Einstein had when he was 16 years old. He imagined chasing a light beam to supply what we know about time dilation. We said, the faster you move, the slower time ticks for you. If you go 99% the speed of light, a year for you is 7 years for the Earth. If you go 99.999%, a year for you is 1,000 years for the Earth. Now take it to the limit. If you hit 100%, if you hit C, time stops. 0, for a photon, time does not pass. It leaves the surface of a star in the Andromeda galaxy. It travels for 2 million years through the void. It hits your eye on a Tuesday night. To us, that trip took 2 million years. To the photon, it was instant. The moment it was born, it hit your eye. The birth and the death were the same moment. For light, there is no distance. There is no time. The universe is a single point of contact. This is a profound thing to think about. We think of the universe as this vast, lonely place full of empty space. But for the light that connects us, the space doesn't exist. Light stitches the universe together. It brings the news of the stars to us instantly from its perspective. So why is light so fast? Because it is the messenger that transcends time. Because it has stripped away all the weight of matter so that it can show us the structure of space-time itself. So we have this speed limit, 186,000 miles per second, 300,000 kilometers per second. It's a big number to us. But on the scale of the universe, it's actually kind of slow. Think about it. It takes light 100,000 years just to cross our own galaxy. The Milky Way, just one island of stars. If you tried to call someone on the other side of the galaxy, you'd say hello. And 100,000 years later, they'd hear it. Then they'd say hi, and another 100,000 years later, you'd hear it. It's a terrible way to have a conversation. So why is the limit so slow? Why does the universe have such a lack? Well, Let's look at what c really is. We call it the speed of light, but that is bad branding. It's false advertising. Light is just the most famous thing that travels at that speed. But gravity travels at that speed too. If the sun vanished, Earth would orbit the empty spot for 8 minutes before flying off. Gluons, the particles that hold the nucleus of the atom together, they travel at that speed. Anything that has no mass travels at c. So c isn't a property of light. It is a property of the fabric of space-time. It is the conversion factor. You know how you can measure distance in inches or in centimeters? And there is a number 2.54 that converts them. Well, Einstein showed us that space and time are the same thing. They are just different directions in the same map. But we measure space in meters, and we measure time in seconds. We use different units because we are biological creatures who perceive them differently. The speed of light, c, is just the exchange rate. It tells you how many meters of space are equal to 1 second of time. And the answer is 300 million meters equals 1 second. That is the ratio of reality. So asking why is light that fast is like asking why are there 100 pennies in a dollar? Because that's the exchange rate. Now, I want to talk about something that really bothers people. They say, okay, I get it. Light is fast, but why can't I go faster? Why can't I build a rocket that pushes harder? If I'm going 99% the speed of light and I fire a thruster, I must go faster. And the answer is, you do, but you don't go faster through space. You go faster through time. Wait. Let me back up. This is the most beautiful idea in relativity. It's called the four velocity. Imagine you are in a car. You can drive north or you can drive east. If you are driving purely north at 60 mph, you are making zero progress east. If you turn the wheel and drive northeast, you are now moving a little bit east, but you have slowed down your progress north. You traded some north speed for east speed. Now Einstein says everything in the universe, you, me, this cup of coffee, we are all moving at the speed of light all the time. But we are moving at the speed of light through space-time, the four-dimensional map. Right now, you are sitting in a chair. You are not moving through space. Your speed in space is zero. So all of your speed is being used to move through time. You are traveling through time at the maximum possible velocity. That's why you're aging. You are hurtling into the future at the speed of light. Now imagine you get in a rocket ship. You start to move through space. You are turning the wheel. You are diverting some of your velocity. You are taking it away from the time direction and putting it into the space direction. So, because you are moving through space, you must move slower through time. That is time dilation. That is why the astronaut ages slower. He isn't experiencing magic. He is just changing his direction in space-time. Now, what happens if you put all your speed into space? You turn the wheel all the way. You use 100% of your velocity for spatial travel. Well, if you use 100% for space, you have 0% left for time. Time stops. And that is what light is. Light is something that has rotated its velocity entirely into the spatial dimension. It has no speed left for time. So you can't go faster than light through space because you can't be more than 100% committed. You can't drive north faster than 60 mph if your car's top speed is 60 mph. You are already maxed out. We are all traveling at CG. Light just happens to do it horizontally while we do it vertically. Doesn't that make you feel a little better? You aren't slow. You are just moving in a different direction than the light beam. You are a time traveler. Now let's get back to the why. Why do we have mass? Why are we stuck in the slow lane? If everything is naturally moving at c, what slows us down? This brings us to the Higgs field. They are a very modern discovery. Peter Higgs and his friends predicted it in the 1960s, and we found it in 2012. Imagine the universe is filled with a thick syrup, or a room full of people at a cocktail party. This is the Higgs field. It's everywhere. Now, some particles, like the photon, they are like ghosts. They pass through the cocktail party and nobody notices them. They zip through the crowd at top speed. But other particles, like the electron or the quarks that make up your body, they are popular. As they try to move through the room, the people at the party cluster around them. Hey, look, it's an electron. They clump. They interact. They slow it down. This clumping, this resistance is what we call mass. Mass isn't a thing you have. Mass is a measure of how much you interact with the background field of the universe. You are heavy because you're swimming through molasses. If we could turn off the Higgs field, snap instantly, all your atoms would lose their mass. And what would happen? You would explode. Well, not explode like a bomb. You would cease to be solid. All your particles, the electrons, the quarks, they would suddenly accelerate to the speed of light. They would fly apart. You would dissolve into a spray of radiation moving at sea. Biology would be impossible. Chemistry would be impossible. Atoms wouldn't hold together. So the reason we are here, the reason we can sit and think and drink coffee, is because we are slow. We are the sluggish ones. We are the ones that got stuck in the syrup. And thank God for that, because complexity needs time. Structure needs stability. If everything was flying around at the speed of light, nothing could ever settle down to build a DNA molecule. Nothing could ever build a brain. The slow lane, the world of mass, is the only place where life can exist. So we shouldn't be jealous of the light. The light is fast, but it is dumb. It can't stop. It can't think. It can't feel. We pay a price for our existence. We are heavy. We are slow. We are trapped in time. But the reward is that we get to be real. We get to be solid. Now let's talk about what happens when light does interact with matter. Because I said light always travels at sea. And that's true in a vacuum, in empty space. But you know that light slows down in glass or in water. That's how lenses work. That's how your eyeglasses work. The light hits the glass and they slows down, bends and focuses. But wait a minute, didn't I just tell you that light can't slow down? That it must go at sea? Am I lying to you? No. This is where the atomic picture is important. Imagine the photon entering the glass. The glass is full of atoms, electrons. When the photon comes in, it hits an electron. Look, the electron absorbs the photon. It swallows it. The electron gets excited. It jiggles. It holds on to that energy for a tiny, tiny fraction of a second, a delay, and then it spits it out. It creates a new photon, identical to the first one, and sends it on its way. That new photon travels at sea until it hits the next atom. Oh, absorbed, pause, spat out. So the light between the atoms is traveling at the speed of light, fast, but the process of stopping and shaking hands with every atom along the way, that takes time. It's like a train that goes 200 miles an hour, but it stops at every station. The average speed is slow, even though the train is fast. In diamond, light slows down to less than half its normal speed. Because diamond is a very crowded dance floor, the photons spend a lot of time shaking hands. This is beautiful because it shows that the slowing of light is actually an illusion of the crowd. The individual photons never slow down. They just get distracted. Now, I wanted to talk about the cosmic implication of this speed. We look at the universe. It is huge. The observable universe is about 93 billion light years across. But the age of the universe is only 13.8 billion years. Wait. How can it be 93 billion light years wide if light only had 13.8 billion years to travel? This is the expansion. Space itself can stretch. And here is the kicker. Space can stretch faster than light. The speed limit c applies to things moving through space. It does not apply to space itself. So right now, there are galaxies on the edge of our vision that are moving away from us faster than the speed of light. The space between us and them is growing so fast that their light can never reach us. It's like running on a treadmill that is going too fast. You run and run, but you move backward. Those galaxies are disappearing. They are falling off the edge of the world. Every day, there are galaxies that cross at that horizon and are lost to us forever. We live in a universe that is slowly deleting its own history. If we lived billions of years in the future, the expansion would be so big that we wouldn't see any other galaxy. We would look up and see only our own star. We would think the Milky Way was the entire universe. We wouldn't know about the Big Bang. We wouldn't know about the expansion. We would be lonely. So we are lucky. We live in the Goldilocks era of the universe. We live at a time when the light can still reach it. We can still read the story of the beginning. Let's go back to the human scale. We use this speed. We use it every day. Your GPS, your phone, it talks to satellites. Those satellites are moving fast, and they are high up in gravity. Because of relativity, the clocks on the satellites tick at a different speed than the clock in your phone. They drift by about 38 microseconds a day. That sounds like nothing. Microseconds, all right? But light travels 300 meters in a microsecond. If we didn't correct for relativity, if we didn't understand Einstein, your GPS would be off by 10 kilometers every day. You would ask for directions to the grocery store, and it would send you to the next town. So these abstract ideas, these things about light speed and time dilation, they are the reason you can order a pizza and have it delivered to your house. It is practical physics, but there is one more thing about light. We talked about it being a wave, but we also said it comes in packets, photons. This is the quantum duality. And there is an experiment, a thought experiment, that shows just how weird this speed limit is. It's called quantum entanglement, spooky action at a distance. If I take two photons and I create them together, they can be entangled. They are twin. They share a wave function. If one is spinning up, the other must be spinning down. Now I send one to you and I keep one. You go to Mars. I measure mine. I find it is up. Instantly yours becomes down. It doesn't matter if you're on Mars or across the galaxy. The moment I know mine, yours is determined. Does this break the speed limit? Did a signal travel from me to you faster than light? It feels like it. It bothered Einstein terribly. He thought it meant quantum mechanics was broken. But it turns out no signal traveled. You can't use this to send a message. You can't use it to send a Morse code, because the result is random. I can't force my photon to be up so that yours becomes down. I just measure it, and it's random. So you see a random result, too. There is a correlation, but no communication. Nature protects the speed limit. She allows a connection faster than light, but she forbids information faster than light. It's a loophole, the secret back channel that the universe uses to keep its books balanced, but it doesn't let us use it to cheat the timeline. We can't send a warning to the path. We can't break causality. The speed limit holds. So I told you, rule. I told you that nothing can go faster than the speed of light. And that is true. In a vacuum, in empty space. But you know, physics is a lot like law. There are the laws of the land, and then there are the local ordinances. What happens if we look inside a material, like water or glass? I told you earlier that light slows down in water. It travels at maybe 75% of its vacuum speed. The photons are busy shaking hands with the water molecules, so the group speed is slower. Now, here's a mischievous question. If light is going slow, can we shoot a particle faster than the light? In a vacuum, the electron can never beat the photon. The photon is the champion. But in water, the photon is handicapped. It is running in mud. The electron, if we shoot it hard enough, can actually go faster than the light wave in that water. It's like a speedboat going faster than the waves it creates. And what happens when a boat goes faster than its own wave? You get a weight, a V shape of water trailing behind it. What happens when a jet plane goes faster than the speed of sound? You get a sonic boom, crack. The pressure waves pile up. Well, nature is consistent. If an electron travels faster than light in water, it creates a photonic boom, a shock wave of light. We call it Cherenkov radiation. And it is beautiful. If you have ever looked down into a nuclear reactor pool, and I don't recommend you do it without a badge, but if you see a photograph of the core, it is glowing. And it has this eerie, ghostly electric blue glow. That blue light, that is the sonic boom of the electrons outrunning the light beams in the water. It is the scream of the particles breaking the local speed limit. So you see, you can go faster than light as long as you pick a race where the light is running slower. But let's go back to the vacuum. Let's go back to the real speed limit. I want to tell you the story of a photon's life, because when we ask why is light so fast, we often forget how hard it works to get to us. Let's look at the sun. We see the sunshine. It feels warm on your face. You think, that light just came from the sun. It took 8 minutes. And that's true. From the surface of the sun to your eye at 8 minutes, a straight shot through empty space. But how long did it take that light to get from the center of the sun to the surface? The sun is a nuclear furnace. Deep inside, hydrogen atoms are smashing together. Fusion. When they smash, they release energy. Gamma rays, high energy photon. So a photon is born in the core. It is born moving at the speed of light immediately. Boom. But the core of the sun is crowded. It is dense. It is 150 times denser than water. It is a soup of protons and electrons, packed so tight you can't imagine it. So the photon travels for maybe a centimeter, maybe a millimeter, and whack. It hits a proton, it gets absorbed, the proton jiggles, then it spits the photon back out. But in which direction? Random. It might go forward, it might go backward, it might go sideways. So the photon flies off again, whack, hits another electron, absorbed, spat out, random direction. It is the drunkard's walk. Imagine a drunk man trying to leave a bar, but he takes one step, forgets where he is going, spins around and takes another step, spins around. He moves, but he doesn't get anywhere. This poor photon, it is bouncing billions and billions of times. It is trying to escape, but it keeps getting turned around. Do you know how long it takes to travel the radius of the sun? If it could go straight, it would take 2 seconds. 2 seconds? But because of the bouncing, it takes 100,000 years, sometimes 1,000,000 years. Think about that. The light hitting your eye right now, it was created 1,000,000 years ago, before human civilization existed, before the pyramids, before the Ice Age. But that energy has been trapped inside the sun, bouncing around, desperate to get out for 1,000,000 years. And then finally, it reaches the surface. The photosphere, the crowd thins out, the space opens up, and the photon says, "Free at last." And whoosh, it flies across the vacuum. 8 minutes, and it hits your retina. And its journey is over. It died so you could see the flower in your garden. It's a tragic story, really, but it tells us something important about light. Light is interaction. Light connects things, but it only connects things when it is free to move. And this brings us to the biggest story of all, the story of the whole universe. Let's wind the clock back all the way. 13.8 billion years. The Big Bang. At the very beginning, the universe was hot, unimaginably hot, and dense. It was so hot that atoms couldn't exist. If a proton and an electron tried to hold hands, a photon would come along and smash them apart. No. Too hot. Keep moving. So the universe was a plasma, a soup of charged particles. Now remember what we said about the sun. When you have a soup of charged particles, light cannot travel. It bounces. So for the first 380,000 years of the universe, there was no light. Well, the light was there, but it was trapped. It was a fog, a glowing, opaque fog. If you were there, you wouldn't be able to see your hand in front of your face. The light would scatter off the fog before it reached your eyes. The universe was blind, but the universe was expanding. And as it expanded, it cooled. It cooled down. The temperature dropped. And finally, it hit a magic number, about 3,000 degrees, the temperature of a dull red light bulb. At that temperature, the photon became just weak enough, just gentle enough that they couldn't break the atoms apart anymore. The proton grabbed an electron. Click. Hydrogen. And the photon came along and bounced off? No. The neutral atom let the photon pass. Hydrogen is transparent. Suddenly, in a cosmic blink of an eye, the fog lifted. The charged soup became neutral gas, and the light, all that light that had been trapped for 380,000 years, was suddenly free. It flew in straight lines in every direction. The universe became transparent, and that light, the light from the moment of recombination, it is still flying today. It has been flying for 13 billion years. But because the universe has expanded, that light has stretched. It started as hot white light, but the stretching of space pulled it like taffy. It stretched into infrared, then it stretched into microwave, and then it's hitting you right now. If you turn on an old television set, the kind with the rabbit ears antenna, and you tune it to a channel that doesn't exist, you see static, the black and white snow. Shh. About 1% of that static is the cosmic microwave background. You are watching the Big Bang. You are watching the moment the universe turned on the lights. It is everywhere. You can't hide from it. If you went to the deepest cave, if you went to the darkest void between the galaxies, you would still be bathed in this microwave glow. It is the afterimage of creation. And the amazing thing is, it is uniform. It is the same temperature in every direction. If I look left, it's 2.7 Kelvin. If I look right, it's 2.7 Kelvin. This tells us that the early universe was incredibly smooth. It was a perfect fluid, but not perfectly perfect. If we look really, really closely, we see tiny splotches, tiny variation. One spot is 2.70001 Kelvin. Another is 2.69999 Kelvin. Tiny ripples in the density. And thank God for those ripples. Because if the universe was perfectly smooth, gravity would have pulled evenly in all directions. Nothing would have clumped. No stars, no galaxies, no us. Those tiny ripples, those little fluctuations in the microwave lights, they were the seeds. Gravity pulled more on the heavy spots. They grew. They collapsed. They became the galaxy. So when we look at that light, we are looking at our own baby pictures. We are looking at the seeds of the structure of reality. Now, I want to pivot a little bit. We have talked about light as a physical thing, a wave, a particle, a speed limit. But we have to talk about color. Why is the world colorful? Why is the sky blue? Why is the sunset red? Why are leaves green? This is all about the interaction of light with matter. It's about the scattering. Take the sky. Sunlight comes in. It is white light. It contains all the colors. Red, orange, yellow, green, blue, violet. But the atmosphere is made of nitrogen and oxygen molecules, small particles. Now there is a rule, Rayleigh scattering, that says small particles like to scatter short waves. Blue is a short wave. Red is a long wave. So when the sunlight hits the air, the red light goes straight through. It ignores the air molecules. It drives right past. But the blue light, it hits the molecules and bounces. Ping, ping. It gets scattered in every direction. So when you look up at the sky, away from the sun, what do you see? You see the blue light that has been scattered sideways toward your eye. The sky is lit up with the scattered blue waves. But what happens at sunset? The sun is low on the horizon. The light has to travel through a lot more air to get to you. It's going through the thickest part of the atmosphere for hundreds of miles. By the time the light gets to you, all the blue has been scattered away. It's gone, filtered out. So what is left? The reds, the oranges, the survivors. The sunset is red because the blue got lost along the way. It's just physics. But it produces the most beautiful painting in the world every single night. And what about the green leaf? This is biology making a choice. Plants eat light, photosynthesis. They take the photon and use its energy to break water and make sugar. But they don't eat all the light. Chlorophyll, the magic molecule, it loves red light, and it loves blue light. It eats them up. But green light, it says no thanks. It reflects the green. So when you look at a forest, you are seeing the wasteland. You are seeing the leftovers. The plants are rejecting the greenness, so that's what hits your eye. Now here is a question. Why? Why don't plants eat the green too? Why waste it? The sun puts out plenty of green light. There are theories. Some say that early life of purple bacteria ate the green, so the plants had to evolve to eat the rest. But nature is funny. Sometimes she isn't perfectly efficient. Sometimes she finds a solution that works, and she sticks with it. Good enough is a very important principle in evolution. And our eyes, why do we see this specific spectrum? Why don't we see radio waves? Why don't we see X-rays? Look at water. We evolved in the ocean. We are made of water. Radio waves, water absorbs them. That's how your microwave oven works. It uses radio waves to heat the water in your food. UV rays, water blocks them. But visible light, the colors of the rainbow, water is transparent to them. There is a window in the absorption spectrum of water. So naturally, our ancestors evolved eyes that worked in that window. We see the light that gets through the water. If we evolved on a planet made of methane or silicon, we might see entirely different color. We might see an infrared. So our perception of reality, the fact that we think light is this brightness we see, is purely a biological accident. We are tuned to the frequency of our environment. And this brings me to the idea of the invisible world. Because we only see this tiny sliver, we often forget how much we are missing. If you could see radio waves, the night sky would not be dark. The center of the galaxy is screaming in radio. The black hole at the center, Sagittarius A star, is blazing bright in the radio spectrum. If you could see gamma rays, the sky would be filled with violent bursts, hypernovas exploding. If you could see microwaves, the whole sky would be glowing white from the Big Bang. We walk around thinking the night is dark, but it isn't. The night is bright. We are just wearing sunglasses, very, very dark sunglasses called human eyes. Science allows us to take the glasses off, but we build machines, radio telescopes, X-ray telescopes that let us see the universe in its full glory. And every time we open a new window, every time we look with a new frequency, we find something new. We found pulsars. We found black hole. We found the afterglow of creation. All because we realized that light is more than just what we can see. So we have come a long way. We talked about the speed of light being a constant. We talked about mass being a drag. We talked about the colors of the sunset. But there is one more thing. The thing that keeps me up at night, the death of now. We all have this feeling, this intuitive feeling that now is a universal thing. We feel that right now, at this exact moment, something is happening on Mars, and something is happening in the Andromeda galaxy. We imagine a giant cosmic clock ticking away, synchronizing the whole universe. Tick-tock. Newton believed in this clock, and he thought time was absolute. He thought now was the same for God as it was for man. But Einstein, that troublemaker, he showed us that this is an illusion. If light takes time to travel, and if the speed of light is the same for everyone, then simultaneity is dead. Let me give you an example. A train. I love trains. Physics happens on trains. Imagine you are standing on a platform, and a train goes zooming past you at a significant fraction of the speed of light. Fast. Now imagine two lightning bolts strike. One hits the front of the train, one hits the back. You, standing on the platform, you are exactly in the middle. And the light from the front bolt and the light from the back bolt reach your eyes at the exact same instant. You say, aha, those two lightning strikes were simultaneous. They happened at the same time. Fair enough. But what about the guy on the train? He is sitting in the middle of the train, but he is moving. He is moving toward the front bolt and away from the back bolt. The light from the front bolt has less distance to travel to reach him because he is rushing to meet it. The light from the back has to catch up to him. Since light travels at a constant speed, the light from the front hits him first. The light from the back hits him later. He sees the front strike happen, then a pause, then the back strike. He says, they were not simultaneous. The front one happened first. Now, who is right? Is it you or the guy on the train? Common sense says, well, I am standing on the ground, so I am right. No? He is moving, so he is confused. But remember relativity. There is no standing still. The Earth is moving around the sun. The sun is moving around the galaxy. From the train guy's perspective, he is standing still and you are the one moving backward. So you are both right. For you, the events were simultaneous. For him, they were sequential. This means there is no universal now. Now is a slice of cheese. Bear with me. Imagine the universe is a giant block of cheese, a loaf of bread, the block, universe, length, width, height, and time. You, standing on the platform, you slice the cheese straight down. Your knife is your concept of now. In your slice, the lightning bolts are next to each other. But the guy on the train, because he is moving, he slices the cheese at an angle. His slice includes a bit of your future and a bit of your past. This leads to a terrifying conclusion. If I can move fast enough, I can change the angle of my slice so much that my now includes events that haven't happened to you yet. Or someone in the Andromeda Galaxy, if they start walking toward Earth, their now might include next Tuesday on Earth. If they turn around and walk away, their now might include last Friday. This suggests, and this is the hard pill to swallow, that the future is already there. The block of cheese exists. The past, the present, the future. It is all one solid chunk of space-time. The dinosaurs are still there in the past. Your great-grandchildren are already there in the full. We are just spotlight beams, crawling through the block, illuminating one slice at a time and calling it now. We feel like we are changing the future. But physics suggests the script might already be written on the film. And the speed of light? It is the geometry of the block. It is the rule that connects the slices. This brings us to time travel. If the past and future are real, can we go there? Can we build a DeLorean? Well, if you look at the equations, if you go faster than the speed of light, you start to move backward in time. Remember the graph? Space on one axis, time on the other. The speed of light is a 45-degree line. If you go faster than that line, you tilt out of the future cone and into the past cone. So if I could build a ship that goes 2 times light speed, I could fly out to a star, turn around, and come back before I left. I could kill my own grandfather. I don't know why physics students are always so violent with their grandparents, but that's the example. If I killed my grandfather before I was born, then I never exist. So I never built the ship. So I never killed him. So I do exist. Paradox. The universe hates paradoxes. It hates logical contradiction. And this is the strongest argument for why the speed limit is absolute. The speed of light is the causality protection speed. It prevents the universe from eating its own tail. It ensures that the cause always comes before the effect. If you break the speed limit, you break logic, and the universe seems to value logic above all else. So you can't go faster than light. Not because the engine isn't strong enough, but because it would break the story. But I want to end on a note of unity. Because this speed, this C, it did something wonderful for physics. It united things that we thought were separate. Before Einstein, we had energy, and we had math. 2 different books, but C tied them together. I know E equals mc squared. Energy is mass times the speed of light squared. Mass is just frozen energy. You are made of frozen light. The atoms in your body, the protons, most of their mass comes from the energy of the quarks zipping around inside. You are a container of energy. And before Maxwell, we had electricity and magnetism. Relativity showed us they are the same thing. Think about a wire, a copper wire with current flowing. The electrons are moving. If you put a compass next to it, the needle moves. Magnetic field. But why? Well, imagine you are an electron moving along with the current. To you, the electrons in the wire are standing still. But the protons in the wire, the metal itself, are moving backward. Because of relativity, the space between the moving protons shrinks. Length contraction. So the wire looks positively charged to you. It pushes you away. That push, that electric repulsion caused by relativity, is what we call magnetism. Magnetism is just electricity plus relativity. It is all one thing. Space and time, energy and mass, electricity and magnetism. They are all facets of the same jewel. And the speed of light is the refractive index of that jewel. It is the constant that ties the universe together into a single, coherent picture. So why is light so fast? It is fast because it is weightless. It is fast because it is the messenger of reality. It is fast because it is the boundary of the present moment. But mostly it is fast so that we can be here. If light were instantaneous, there would be no past, no future, just a chaotic instant. If light were slower, the universe would be dark and cold, unable to communicate. It is exactly the speed it needs to be to allow for a universe that has structure, history, and meaning. And we, us humans, we are the lucky ones who get to sit in the middle of it. We are slow. We are heavy. We are stuck on a rock. But we have minds that can race at the speed of light. We can look at a photon that has traveled for 1 billion years and understand its story. We can capture the light in our telescopes, in our cameras, in our eyes. And in doing so, we verify our existence. We are the universe looking at itself, using the light as a mirror. So the next time you look at the stars, or the next time you just flip a switch in your living room, don't just take it for granted. Think about that messenger. Think about that photon. Think about the 1,000,000-year journey it took to escape the sun. Think about the 8 minutes of freedom in the void. And think about the fact that it ended its journey on your retina just so you could see. It's a gift. Keep looking, keep wondering, and remember, nature has a great imagination. She is